Oh yeah, so I'm Mark Wong. I work for Second Quadrant. I'll give a little background of what I'm looking at, describe some of the patches I've been evaluating. I'll describe the tests I've been running on these things and give you a look-see at what the results look like. So the European Union sponsored this AXL project, where AXL stands for the Advanced Analytics for Extremely Large European Databases. The objective of this project is to increase our ability to make decisions on real-world data. So AXL wants to be able to do this using open source software like the Postgres database, and Orange, which is, I think, a set of tools for data visualization. So I'm primarily focused around the scalability parts, but the AXL project also goes over, or tries to cover security, privacy, auditing, visual analytics, and taking advantage of advanced hardware features such as vector instructions on these newer processors that we have these days. So the other folks that are involved in this, including Second Quadrant, is the Barcelona Supercomputing Center, Porta Vita, which is a healthcare company, the University of Manchester, and the University of Ljubljana. I don't know if anyone can help me pronounce that. Good. So these are the patches I've been looking at. All these are intended to help the performance on larger database systems, and later you'll see what large may or may not be. One of the features that has already been committed is BRIN index. A couple other patches that are still being reviewed include a concurrent hash table for buffer lookups, and to reduce the lock contention around acquiring lightweight locks in Postgres. So BRIN stands for block range indexes. It's a new to Postgres type index. This was authored by Alvaro Herrera, which is at Second Quadrant, based down in Chile. For those of you who take a look at the hackers mailing list every so often, you may recognize this as originally proposed as min-max indexes. So the BRIN indexes are intended for big data type systems, and for those of you who are familiar in the Oracle world may recognize these as the Exadata storage indexes. So why would you want to use BRIN? It is a smaller and less costly to maintain index compared to B trees. And because of this, it allows you to use an index on a table that may have been impractical with a B-tree index. Does anyone ever have to deal with tables that big that they couldn't create a B-tree index? So this is intended to allow you to use an index on a large table without having to break it down with horizontal partitioning and whatnot. And to give you an idea of the optimal scenario for using a BRIN index, imagine it's supposed to work best in the case where you have a column that has a linear sort order. You can imagine having a table recording sales orders, for example, and one of the columns is the date of when an order was placed. Hopefully it's easy to imagine that as you're inserting rows in this table, that date column will be continually increasing as the table grows. So conversely, BRIN indexes are not as useful on columns where data is scattered and randomly ordered for practical purposes. This is just a little visualization of what a BRIN index looks like compared to a B tree. I imagine many of you are familiar with what a B tree looks like, where you have a tree structure and you traverse the tree to find values. So in this example, you know, at the root of the tree, there's 7 and 16. If there's a value less than 7, you go off to one side, the left side. Anything between the 7 and 16, go down the middle, and everything greater than the 16, go down to the right. With a BRIN index, the pages in the index are such that each page will have a reference to what the minimum value of all the data that's being referenced in that page and what the max value is. So when you're looking for a particular value, you just traverse down the pages in the BRIN index until you find the page that is supposedly holding the value you're looking for. The patches which are a little more, affects things a little more behind the scenes include this concurrent hash table, which is authored by Robert Haas at Enterprise DB. It's intended to improve the concurrency of accessing the buffer table between simultaneously running queries. And it does this by using memory barriers instead of locks to look up values, and atomic operations when inserting and removing values from the buffer table. A series of changes around the lightweight locks, specifically the shared lightweight lock as opposed to the exclusive one, is authored by Andres Freund, who's also at Second Quadrant, based out in Germany. It is intended to reduce contention around acquiring these locks by using atomic compare and exchange instructions to grab a lock, and takes advantage of that to also provide a lockless clock sweep algorithm for evictions from the buffer table. And also, is anyone familiar with fault sharing? Hardware stuff? All right. So one of the other changes that is going on is that we're increasing the padding between the locks to reduce the fault sharing of between processors for these locks. So I provide a little graphic. I find the hardware aspects of parallel systems kind of interesting. So at the bottom is a representation of the memory of the system. The grayed out boxes out there, if you can imagine, is what would fit into a cache line on a processor. So if we imagine that each of those blocks represents a lock that a process might want to acquire. The fault sharing is a situation where we'll take CPU 0 wants to get the red lock, so it loads that chunk of memory into the cache line. Then at the same time, something running on CPU 1 wants the blue lock, which is right next to the red lock. And before it can load that cache line, it needs to write it out from CPU 0 back out to main memory, or the cache line on that CPU 0, before it can load it into its own cache line and access that. So if CPU 0 is not done yet, it wants that cache line back. And I think some people call this hot potato effect with processors. And in parallel, well, at least in database workloads, this padding of data structures seems to have a much bigger impact than being able to cram data into a single cache line. So to give you an idea of what the hardware is that we're testing this on, we have a system that's hosted by the Barcelona Supercomputing Center. It's a 2-socket system, and I want to emphasize that for these patches to improve scalability, the number of sockets you have in the system is going to make a bigger impact than the number of cores you have total. So this system also has 256 gigabytes of RAM and 120 terabytes of fiber channel storage. There's also a slightly different system being hosted at the University of Manchester. This one has 4 sockets in it, also has 256 gigabytes of memory and 10 terabytes of SSD storage. So on to the test. What the folks in the Axle project want to see is some improvements to the TPC BenchmarkTMH. Anyone familiar with TPC? So the TPC is the Transaction Processing Performance Console, composed of many of our database friends like Oracle, SQL Server, and Formix, and DB2, and our popular hardware vendors, including IBM and HP. So they published this specification. This particular one, I think, was published in '99, which is derived from another one that was actually published a few years before that. But this specification describes a suite of business-oriented ad hoc queries against a part supplier data warehouse. It is composed of 3 parts: a load test, a power test, and a throughput test. I'll go into those in a little more detail in a bit. And we want to evaluate the BRIN indexes with some more specialized, focused microbenchmarks, so we can get an idea of I guess, simple differences between the performance on the BRIN indexes compared to B-tree, which may or may not be apparent in this larger H workload. So the load test is simply a measurement of how long it takes to load data into the 8 tables that are defined, and the creation of all the indexes that will be used in the other 2 tests. So the way we run this test is to start the load of each of the tables simultaneously. And then once the data is loaded into each table, then all the indexes are created simultaneously for that table. So our expectation for the patches we're evaluating in this is that the combination of the BRIN index and the scalability patches will ultimately reduce the index creation portion of the load test. The power test represents the raw query execution power of a single user. There are 22 different queries defined and are executed consecutively. The orders of the queries are randomized per test. The test is scored by taking the geometric mean of the execution time of each query. So in the power test, what our expectation was is that the use of BRIN indexes will be at least comparable to B-tree indexes and actually hopefully better when the database grows big enough. To give you an idea of what some of these queries look like, query 14 monitors, it's supposed to give an idea of the market response to sales with promotions attached to them. So this is calculating a percentage of the revenue generated from a sale from everything that has a promotion attached to it, compared to what all the sales were for a particular part over the course of a month. One of the other queries I threw in here, query 12, is trying to determine whether using less expensive shipping methods is negatively affecting the ability to deliver parts on time. So this is taking a count of how many urgent and high priority parts were ordered versus non-urgent and high priority counts for particular shipping modes where the delivery date was after when the order was supposed to have been received. And again, over the course, in this case, it's over the course of a year. And finally, the throughput test is the measurement of the system's ability to execute multiple queries from simultaneously from multiple users. The way this is run is by executing multiple power tests simultaneously. In TPC-H terminology, each of these instances are referred to as a stream. The way that this test is scored is by taking the ratio of the total number of queries that were executed between all the streams to the amount of time it takes to run all of them. So we're hoping here that the patches to help with scalability will improve our ability to run multiple streams and also the number of queries that are actually executed, or to improve how fast the queries are executed. Now, describe a little bit of the microbenchmarks that we created around measuring how well these BRIN indexes work. What we'll do is we'll see how long it takes, see what the impact is when we load a table with indexes already in place, how fast we can create indexes, and what the overhead is on maintaining that index as the table grows. So we'll take the line item table out of the specification, which has 6 million rows per scale factor. So for example, at the 10 gigabyte scale factor, we'll have 60 million rows. 100 gigabytes, we'll have 600 million rows, and so on. So the comparison we make with loading a table is we'll take a baseline and see how long it takes to load 8 gigabytes of data, 60 million rows, into a table without any indexes. Then we will create a B-tree index on one of the date columns and see how long it takes to load data into that, and then repeat that with a BRIN index instead of a B-tree index. For timing the index creation, we'll take a table, load it up with data first, and just see how long it takes to create a B-tree index on that same date column. And again, how long it takes to create a BRIN index. The way we try to measure the maintenance overhead on an index is we'll establish a baseline by taking a table without any indexes, take that same 60 million rows of data, and we will see how long it takes to keep loading that into the table until the table reaches a terabyte in size. We'll repeat that with a single B-tree index on the date column, and then once again with a BRIN index on the date column. So on to the results. We'll take a look at the BRIN microbenchmarks first. So at that 10 gigabyte scale factor where we're dealing with 60 million rows, without any indexes takes about a little over 5 minutes to load that table. with the BRIN index, it increases that load time by about 10%, at another half a minute. And the B-tree index actually takes about 9.5 minutes, more than 80% slower to load than if there were no index in place. When creating an index at the same scale factor of 60 million rows of data, B-tree index takes about 95 seconds. BRIN index takes about 18. So about a 80% difference with just only 60 million rows in the table. The overhead comparison, the very bottom line is the timings of loading that table without any indexes. The orange line just above it is the timings from having that one BRIN index on the date column. I think visually you can see that over the growth to 1 terabyte of data, that the overhead seems pretty consistent as that table is growing with the BRIN index. The very top line represents the timings from having that B-tree index instead of the BRIN index in place. While the slope of that line may not be very high, I think it's visually apparent to see that as the table grows, that overhead of the B-tree index is slightly increasing. So now we'll see how this impacts the bigger TPC-H tests. Now at the 30 gigabyte scale factor, when we're using all B-tree indexes, we're building 28 of them across the 8 tables, and the time it takes to load all that, to load the 30 gigabytes of data and create all this index takes about 46 minutes. In the extreme case where we replace all the indexes where we can use BRIN, we add 8 BRIN indexes, reduce the number of B-tree indexes down to 21, and we ultimately have one more index than we did before. But the total build time drops down to 34 minutes, about a 25% improvement by changing only about a third of the indexes. So for the power test at 30 gigabytes, well, for the power test in general, 15 of the 22 queries that are executed will attempt to take advantage of a BRIN index. I've listed these out for reference later. But on the graph comparing just those queries where BRIN index is used, we'll see in one case that BRIN index actually helps one of the queries run faster. In most of the cases, having the BRIN index is a little bit slower. And in a few cases, it seems to be quite a bit slower, maybe twice as slow. Now, at the 100 gigabyte scale factor, what we see is that there are a couple of queries where the execution time with having those B-tree indexes start to rise more dramatically, while the execution time with the BRIN indexes are not seeing quite a dramatic change in execution time. How many people deal with more than 100 gigabytes of data? Yeah, so hopefully this will be encouraging for you. Summary of the numbers at the 30 gigabyte scale factor, the overall score with the BRIN index ends up being about 15% smaller than having the B-tree index. But at the 100 gigabyte scale factor, the score of the BRIN index stays about the same, whereas it starts to drop dramatically for having just B-tree indexes by almost 30%. Another sanity check that we wanted to do was to see what happens, or see what the comparison is when we don't have any indexes on the table. Have people find themselves in a situation with those large tables that they're better off not trying to build any indexes? So one thing to note, though, is in the red bar is representing the execution times with without any indexes. I capped the statement timeout to 3,000 seconds. I wasn't really willing to wait any longer than it took to run the slowest query with the B-tree index. So in 3 cases, these queries took a very long time to run without any indexes. What's interesting to note is that in some cases, having no index for some of these queries seems to can run a little bit faster than even having a B-tree index. But in other cases, we happily see that having some index on a table is actually improving the query performance.
Are you using pertinent indexes?
Yes. The way that this benchmark is actually supposed to run is that you're only supposed to have primary key indexes and indexes on foreign key columns. What we've done to make things run faster is to add additional indexes on top of that to try to get as good of a execution time as we can. So just looking at the scoring for the power test at 100 gigabytes, it's greater than a 70% difference with having the BRIN indexes versus having no indexes, and that score would probably be lower if I had let those queries run to completion, which would quite adversely affect the calculation of the score. So overall, I think we can feel that our objectives with the BRIN indexes have been met. The size of a BRIN index is also over 600 times smaller than a B-tree index. On that table with 60 million rows, the BRIN index is only about is just under 2 megabytes, whereas the B-tree index will be about 1 gigabyte. And just to reiterate that, I think we've seen that the overhead of having the BRIN index, the maintenance, the size is all improved over a B-tree. And while it's unfortunate that it looks like BRIN indexes are a little bit slower at smaller table sizes, as those tables start growing, we're hoping to see a bigger gap between how well a BRIN index will help your queries over a B-tree index. So now we'll take a look at to see how our scalability looks, or how well the scalability is improving. So if we look at the load test, because we're executing those index creations simultaneously, we see that comparing to 9.2, 9.5 without the patches and 9.5 with these patches, we see a 20% improvement on the overall load test with just infecting the index creation time, 20% change over since 9.2, and still almost a 15% change from the addition of those patches to the 9.5 tree. So on a 2-socket system, the bottom line represents the throughput score as the number of streams grow, the number of simultaneous power tests that we're running. That 9.2.
How many cores?
This is I'll have to do that in my head. Or actually, I have to look it up first and then do it in my head. So 8 cores per processor, 16
real cores, 32.
Right, and then just in case you ask about the next one, that 4-way is 8 cores and 32 threads. All right, so we see with 9.2 that we peak about having 14 simultaneously running streams at the 10 gigabyte scale factor. The top line with 9.5 in the patches, while the higher line indicates that the score is higher, we still don't seem to improve much beyond around 14 streams running. But on a 4-socket system, 9.2 again on the bottom, still peaks out at about 14 streams. Can't get much more throughput out of that system. But with 9.5 and those scalability patches, we seem to peak around having 20 streams running in the throughput test. So how many people have more than 2 cores on their system? All right, or 2 processors, I should say. So something else that you can hopefully look forward to with the 9.5 release. Then finally, just a little bit of history of how well the power test has been running over at the 100 gigabyte scale factors in this 9.2. We can see that even in the power test, as we've been releasing versions of Postgres, that the score has been improving a little bit over time. And the addition of these scalability patches seems to help the individual single stream case also. And that's all the data I've collected so far. Are there any questions? Yes?
So you're focusing mostly on looking at the BRIN index with regard to really large databases, but with the smaller index footprint, would you also expect BRIN indexes even on smaller tables if you had much more constrained shared memory to have any effect if you had very small amount of shared buffers?
Yeah, so the question is, I guess to rephrase slightly, to see with smaller data sets how much we can expect the BRIN indexes to. Particularly
if you're on,
memory, like a constrained, resource constrained system, yeah.
Take much less memory to be able to hold a higher index.
Unfortunately, I don't think I know the internals too well to be able to answer that very well. But yeah, I will admit that the focus has really been on the large tables and having lots of resources. Yes?
2 questions about BRIN indexes. Number one, in some of the queries you showed that there were actually queries where the B2 index was faster than the BRIN index.
Yes.
Do we have any kind of a cost model for the BRIN indexes at this point, where the planner would actually choose the correct index if you had both available?
I think a little bit of effort has been looking into that, because when we look at the analyze, the explain analyze, we are seeing a lot of disasters, planning disasters in some of those cases, and I think we have someone trying to narrow that down to see if we can improve that. I got a 1-minute warning.
The other question about BRIN indexes is, have you had a chance to do any test cases where the B-tree index does not fit in that? I would think that would be where you would see the real difference.
Yeah, that is a good point. I think if I were to comb through the data, I could see that, but I don't know that offhand. One last question? All right, thank you, everyone. Oh, sorry, we had one question.
When you create a table in Postgres, you can specify free space on the row level, like I think it's like 7 to 9%.
Mm-hmm.
Does it have any impact on the BRIN index?
I don't know if anyone can correct me, but for some reason I don't think that you can specify that for the BRIN index. There are some other aspects of the BRIN indexes, for example, how many pages you have in each range of pages of the index that you can specify, but I don't know offhand whether you can specify that, the free space. All right, I think that's all the time I have. Thank you.